Hi everyone, can you hear me? How many engineers here? How many people are engineers? I've got bad news for quite a lot of you guys. It's going to be interesting. Actually, the world is changing, and the way engineers look at the world is also changing. Anyway, here we are. All right, to start with, let's talk about the reason why there's a big race to change, why we have to change very quickly in terms of what we do. Climate is changing. We've seen the results of climate change in Australia, in India as well, with the climate becoming far warmer in the summers and far colder in the winters. The cost of energy in India is rising. Our population is rising. It'll start to stabilize and plateau, but it's changing. And India is urbanizing, so it gives us a real big opportunity here to think about the way we solve problems very differently, and that's really what I'd like to talk about. Thinking about that. So, if I just look at the electrical grid itself, uh, back from when Nikola Tesla invented the present AC grid to pretty much 1990s, the grid was a very simple thing. There were big generators, power was then moved to people who consume power. Nowadays it's changed. Now everything is very complicated. You have cars, you have solar power, you have wind power, you have distributed generation, you have large generators, and it's a lot more complicated to understand what's going on and how to run the system most effectively and efficiently. So fundamentally, if you look at the differences, and for me, the key element about how we're going to change as a society of engineers, problem solvers, is we have to change by practice. We have to change by doing things differently and learning while we're doing. So the future grid, very simply, is multi-directional. Flow is changing. Distribution is now not just uh, about consumption, it is also about generation. One other area where things have changed dramatically, which is data is available from every part of the grid. Earlier, data was available, but generally at transmission level. Now we have data available at transmission, distribution, consumption, generation, and at real time. Thank you. So, the duck curve was invented by people in California, and fundamentally it showed how consumption changes through the day. And really, with the introduction of solar power, for example, the duck curve started to become much steeper, and it has become a lot harder to viably, economically run the grid, to run generation, to make sure that you have enough generation to be able to deal with the peaks as well as with the base loads. So the way we have to think about the grid now, and the way the grid is being thought about, is being able to change both consumption and to be able to change generation. Fundamentally, that's looking at doing five different things with the duck curve. You can flatten the back, kind of try to pull that up a little bit. You can lower the head, you can lower the tail, or you can generate more, which is not very efficient. And finally, you can adapt fast. So in reality, you have to use kind of all five of these. And for the grid to understand how to use all five of these, for us to be able to put the control mechanisms in place, to be able to understand and analyze the data, that is really what the challenge for the grid is today. And that's a challenge that all of us engineers need to collectively come together and fix. So the key with the amount of data that we have or that is being produced is we need to make sense of it. So start of that is we have to sense all the changes that are happening in the grid. So lots of metering, measurement devices, all of that comes together, lots of different data systems coming together. We need to collate that information, look at it from the perspective of big data or lots of databases coming together. Then the next phase, the understand phase. I think this is really where technology is changing now. Where even until 4 or 5 years ago, human beings were doing most of the understanding, the analysis. You needed to have PhDs in mathematics and statistics to be able to figure out what was going on. Now, machine learning and AI is kind of solve that problem for us. And this is really where the challenge for Indian engineers exists. Because we're all fantastic at the understand phase. We've all been trained at the IITs of the world, IITs of India, to be fantastic analysts. Uh, but beyond that, the greatest and the best engineers of us also get to the second part, which is the do phase. And that's really the challenge that Indian engineers are going to face, we're all going to face, in terms of how do we move ourselves from analysis and into doing, because that's really what the new phase of engineering is going to be like. So, data is everywhere. We talked about that. We talked about how data can be used to solve the problems, all five elements of the market. So you have the energy market itself. Even in India now, you're starting to get trading in the market for energy, and you can expect that to expand. Um, Moving forward, when we talk about generation, if we talk about the fact that generation is going to need to constantly change and adapt and be very different from what it used to be, then here again you need to have great sensors and great actuators being able to work through data analytics. Network operations. So both network operations and distribution operations, they are changing because you have power flowing in two directions all the time. And finally, domestic users. The domestic users are actually a fantastic way of helping stabilize the grid, changing the duck curve and making sure that you can maybe move their demand a little bit left and to the right by smart controls, either in terms of thermal controls or in terms of controlling the heavy loads in homes. All of this will only be possible, will only deliver value if we look at the data that we're getting and making sure the volume, which is the amount of data that we're getting, is coming through in an understandable way, that the speed at which we get data is right for the job. Everything doesn't have to be real time. A lot of people focus very much on getting real time data. In fact, you don't need real time all the time, you need at the right time. Finally, you need true data. And more, as you get different sources of data, multiple sources of data, it's becoming harder and harder to rely on the old school paradigm of IT, which was a single source of truth. Now you have multiple sources of truth. How do you make sure you converge them, make them work better? And we are talking about a variety of data. In the electrical grid, you have data coming in from generators, transmitters, IT equipment, distribution companies, from individual users, the whole works. So you have this complicated, convoluted mess of information. The key element for us as engineers is to look at, can we make sense of it all? Can we teach AI and machine learning computers to be able to start to make sense of this all? And that's a big change for us. So if I look at the key areas where engineering is changing, number one, earlier engineers were known to have a lot of knowledge. They had access to a lot of knowledge. We went to engineering school and studied a lot to get the knowledge. Nowadays, all of that's easy, right? You have it all available on the internet. How many of you guys have, been to the doctor and as soon as you left the doctor, Googled the diagnosis the doctor has given? Sometimes you would have done that even before, right? You would go to the doctor and say, "Doctor, I think I have this." The doctor will say, "Yeah, relax, let me have a chat with you." That's really, that's how it's changing, and even for engineering, that's changing. The next element is huge sources of data freely available online. Finally, well, not finally, thirdly, we have quick computation available with us at all times. It's a common theory that Apollo 11, the computing that took Apollo 11 up to the moon and back, we have about 2 times that computing in all of our mobile phones today. We now have the ability to model for forecasting and for prediction, which we didn't really have that much. We also have the ability to design parametrically. So parametric design is a fantastic set of new tools which you put in a bunch of rules into it. system, and it will tell you what the best solution is for that. A lot of our engineers today, whether they're electrical engineers, structural engineers, especially in India, are just that's their day job. Their day job is to just say, okay, these are the 10 constraints I have, and this is the best solution out of those 10 constraints. Unfortunately, all of that stuff was going to be done by computers going forward. That is all helped by the fact that you have good, strong, very capable integrated design packages for all the different forms of engineering. And finally, maintenance is changing. So now you have tools available. You saw some things in the video of AR tools, VR tools available, which make actually maintenance a lot easier. So earlier, even a simple person whose day job it is to be a Xerox machine technician, now he has AR available to him so that he can quickly go and diagnose the problem using AR. So as the world is changing, we need to think about actually how engineers need to apply their knowledge and their problem solving skills in a different way. So, quick detour to cancer research. A friend of mine is working on this in Imperial College, and it's very interesting that now AI has made that changeover. They've made that switch over where AI is faster and better and more accurate at finding breast cancer than human beings are. So fully trained oncologists are less accurate and slower than a computer is. And the reality today is what used to be a two oncologist job. So two oncologists would have to go and check the breast cancer screening results before they said whether you had cancer or not. Today, that's going to shift to one AI expert and one oncologist. So already, one of the highest paying jobs in the medical industry, oncology, that's going to change. And if oncology is going to change, and if oncologists are going to start to lose their jobs or start to have to do things differently, then guys, the same thing's true with engineering. So, where do I think engineers need to go? Fundamentally, engineers have been looking for a long time at the technology element of engineering. The good engineers look at context, what's going on around the project that they're working on or the development that they're doing. Some also look at money. The best engineers add the human element to whatever they're doing. And really, that element is the one element which, at least in my lifetime, is going to carry on being run by human beings. So if I look at that a little bit more, traditional engineering is being taken over by computers and computing, and engineers need to put people front and center. They need to be able to look at three elements which actually traditional engineering education has never taught us. Sociology, how do human interact, how do human interactions with the world actually develop the world? Interaction design, this is how do humans interact with technology. For a long time, this has been in the graphics side of things, in the design school side of things. This needs to move towards core engineering. And finally, service design. Virtually all products nowadays come with a service element attached to it. And we all need to become, as engineers, really capable at service design, understanding and empathizing with the users. So finally, if I look at it, empathy, understanding people, and to be cross-functional, to no longer be just electrical engineers, to no longer be just electronics engineers, but to be able to span the way systems and IT will be able to span. Because that's really the changing paradigm for us as engineers. If we don't do that, then those who are engineers and about my age will probably not have a job by the time I retire. That's critically important. So that's it, guys. Thank you.